Okay, in this video, we want to start looking at chapter 7, which is going to be a chapter on proof by contradiction, which is one of the most important proof methods, I would say, that we're going to cover, because it's, besides, we've covered already some very important methods. Direct proofs, of course, are important. Induction comes up in a lot of different places. Proof by contrapositive is good to know about, but proof by contradiction is perhaps the most common alternative method to a direct proof. And so in order to start talking about this, I'm just going to remind you of some simple truth tables. So first of all, if we have a statement, S for statement, of course, it can be true or false. And this is going to be a very simple truth table. So not S is going to have the opposite values. And then I just want to point out some simple things here. So we can take S and not S, or we can take S or not S. Okay, and S and not S, of course, and requires both to be true. They can't both be true. This is always false, and the other one is always true, because the or just needs one of them to be true, and they'll always both be true. But what we want to notice here is that, well, first of all, no statement and its negation can both be true at the same time. That's what the third column says. And also every statement or its negation has to be true. Now, the way I've written it here, it feels kind of a trivial thing about ands and ors, but this fact about logic, called the law of excluded middle, um, is an important sort of observation that leads to proof by contradiction. And though I don't want to spend too much time talking about this next comment, there has been some disagreement about the law of excluded middle in the discussion of logic, though in mathematics, certainly now there is little to no worry about this particular issue. Okay, but now, since most statements in mathematics are given as implications, we also want to think about how the logic of negation works here. And so I'll give a slightly more interesting truth table. So now we have a P and a Q. And so we fill this out the way we usually like to have every possible combination of P's and Q's. And then just to have some things to work with, we can have not P and not Q. So we just take the opposite of those columns. Okay. And a little bit more significant is we can take the implication definition here. And so we know that that needs to be, the only time that's false is if a true implication implies a false one. And then we want the negation of that. And the last column will be P and not Q. So the negation is just the opposite. So we get false, true, false, false. And then we notice that P and not Q will line up the following way, right? We need both to be true. This would be true and false, so that's false. This would be true and true, so that's true. Then we get false and false, so that's certainly false, and then false and true, which is also false. And the point is that these are logically equivalent. Now, we've seen this before, so I'm just reminding us of this fact that we've done before, but it's going to become very important here in the proof by contradiction. So the way we say this, of course, is that not P implies Q, and P and not Q are logically equivalent. Okay, so when we do a proof by contradiction, we're going to have a statement. It could just be a statement given as just an S where we don't necessarily write it as an implication, but it can also be written as a explicit implication. And the way we're going to prove it is by assuming its opposite. So either we're just going to take not S, or S will be an implication. So when we take not of the implication, we're going to assume P and the opposite of its conclusion, right? And then our goal will be to derive a contradiction from those assumptions. And so that tells us that the not statement can't be correct. And so the original statement must be correct. And it's the law of the excluded middle that tells us that you have to either have S be true or not S, and you can't have both be true, which makes this proof method work, right? If we assume the opposite, derive a contradiction, that means the opposite cannot be true. And there's only one option left, which is the original statement must be true. Okay, so that's the idea. But now that I've mentioned the idea, you have to see several examples of this to really understand what I mean in practice. So let's look at some examples, all right? So first is proposition 7.1, which is that there does not exist a largest natural number. Okay, now this statement might feel silly to you. Maybe you're like, this is clear, right? Um, so, and that's okay if you feel that way. I understand that, but it's still going to be a good example of a proof by contradiction. And for right now, we're just looking for examples of the proof technique. I will say though that although this will feel silly when I'm doing it now, this proof also holds in settings where we don't have good intuition for a particular sort of axiomatic model. So anyway, I won't say more about that, but I just want to say that oftentimes these proofs that feel silly, um, it's because we're proving it in a scenario where we have a lot of intuition for it, so like natural numbers, but these proofs oftentimes also hold in settings where we have almost no intuition, and it really is important to have a proof. So anyway, but for us, I think it's really just an example of a proof by contradiction. Okay, so how do we do this as an idea, right? So P is the statement of the proposition, let's say. So P is the statement, there does not exist a largest natural number. By the way, let's try to write this in quantified language, right? So there does not exist, right? So there exists with a not through it, or maybe I haven't really been using that notation. So let me instead say there does not exist. Let's call it capital N in the natural numbers such that now we have to somehow quantify what it means to be largest, right? So now we need another quantifier. So such that for all little n, which are also natural numbers, n is always less than or equal to capital N. So if I take away the not, then this would say there exists a capital N, which is a natural number, such that for all other natural numbers, the other natural numbers, little n, must be less than or equal to capital N, which would mean that there is a largest one, right? Okay, but I'm saying that there does not, so we put a not in front, right? And so this is the statement P. If I want, I can now send the not through, right? So if I send the not through, I would get for all capital N natural numbers, there exists a little n, a natural number, such that n is strictly bigger than capital N, right? So that's equivalent to saying that there does not exist a largest number. Another way of saying that is for any natural number, you can always find some other natural number which is bigger than it. Okay, good. But the proof technique is going to be assume not P. Okay, and since if I just take the original formulation in logic, well, let me write it in words first. So there does exist a largest natural number. And if I want to write it in quantified form, I can just take my first formulation, hit a knot, and the two knots in the front will go away. So I get there exists an n such that for all n in the natural numbers, little n is less than or equal to capital N. Okay, and the proof strategy is to assume not P and derive a contradiction which shows that not P is false, and so hence P is true. And then that'll be the end of the proof. Okay, so let's look at the proof. And by the way, just from a proof strategy point of view, like, you might say, well, why don't we just try to prove P directly, right? But what's helpful here is that when I go to not P, I get to assume that there is a largest one, and that's something I can work with, right? Oftentimes in a proof, we need something to work with. And so if I assume there's a largest one, I get to play around with that largest one and derive a contradiction. So it's really from a point of view of what can I use and what can I do with it, that a proof by contradiction suggests itself in this case. Okay, so we have to tell the reader that we're going to do a proof by contradiction. So one way of doing that is to say, assume for sake of contradiction. So I'm saying to the reader, I'm going to make an assumption, but I'm expecting this assumption to lead to a contradiction, right? So I'm giving them some commentary about what we're going to do. So assume for sake of contradiction that there is a largest natural number capital N. Okay, so hence for all natural numbers little n, and we know that little n is less than or equal to capital N. Okay, we already said this to ourselves when we were doing the strategy, right? In quantified form. Oftentimes in a proof, we like to write things in words. Okay, so since n is a natural number, we know that n plus 1 is also a natural number. Okay, that doesn't feel too significant, but it's definitely true. So by assumption, remember we said if you have any other natural number, then it must be less than or equal to capital N. So n plus 1 is some other natural number, so it must be less than or equal to capital M, right? Now this is going to be, you already might feel like this is a contradiction. Let's just make it extremely obvious. And so subtracting n from both sides, we find that 1 is less than or equal to 0. And now this is a contradiction because we know by definition that that's not the case. So this is a contradiction. And hence there must not be a largest natural number. Okay, that's it. That's the end of the proof. And that's our first example of a proof by contradiction. Again, I understand that it might feel a little bit silly, but I hope that you at least get, in a very simple proof, some of the structure of what a proof by contradiction looks like. And we're going to build up several more examples, and eventually they're going to get quite more sophisticated. But we want to start with some simple examples to get the idea first.